crystal field theory named as CFT. In valency bond theory, we learn the shapes of the molecules, that is, shapes of the complexes. And it did not give the information about the colors, but all complexes do have colors. About the strength of the bond, they do not give the strength of the bond. They don't explain some abnormal properties which can be explained by this CFT. So there are certain drawbacks in the valency bond theory and certain merits also there. We discussed the merits. The remaining drawbacks were rectified in by this crystal field theory. Crystal itself indicates it is ionic bond. Sodium chloride is called crystal. Potassium chloride is called crystal. Right? Camphor is not called crystal. Camphor is a molecule, or methane is a molecule. So name itself indicates it relates to ionic bond. So crystal field theory explains about only ionic bond between the central metal atom and ligands. So that is the first point. Explains only electrovalent bonds. Electrovalent bonds. What are electrovalent bonds? Nothing but ionic bonds. Ionic bonds. And in this theory, central metal atom is there with the oxidation state with positive or zero. Ligands are also there. The fundamentals remain as such, but the approach differs. All ligands are called point charges. They are called point charges. Why? Because they donate lone pair of electrons to the central metal atom. Hence, they are called point charges. If it is Cl minus or Br minus or hydroxide ion, it appears they are as point charges. That means if you consider negative ligands, so it is very clearly evident that there are certain charges. So hence they are called point charges. Even in case of ammonia or water or ethylene, diamine or whatever the neutral ligands, they are also called as point charges. Why? Because ammonia has a dipole moment. Likewise, you know very well ammonia can be depicted like this. It has a dipole moment. That means the electrons move in this direction. The net charge will be in this direction. So as a result, the total negative charge is in one direction. That directional negative electrons are nothing but point charges. So try to remember, point charges can be applied to all ligands. There should not be any confusion. If it is a ligand, lone pair donor, therefore they are point charges. So ligands are considered as taken as point charges. Point charges. And this theory does not consider any kind of orbital. In previous theory, we have taken the orbitals and we have considered the hybridization also. Likewise, sp3, dsp2, sp3, d2, likewise, I told you in the yesterday class. So, this theory does not consider overlapping of orbitals. Does not consider overlapping of orbitals. And it considers interactions between the central metal ions and ligands. Interactions means maybe attractive forces or repulsive forces. So it considers interaction among the ligands and the central metal ion. Therefore, it considers interactions between central metal ion and ligands. Ligands are nothing but point charges. It can be considered, these interactions can be divided as two types, that is attractions and repulsions. The attraction between central metal ion or atom, central ion atom, and ligands. Why? Because central ion has positive charge, ligand has relatively negative charge. Therefore, positive and negative charges are attracted by what forces? Ionic bond, and they are called attractions. So this is one kind of attraction, and also considers repulsions. Repulsions between electrons of central ion, central atom, and ligands. Why there is a repulsion? Central metal atom has positive charge. For example, if we consider Fe+3, the +3 charge attracts the negative charges. And in Fe+3, there are certain d electron also. 3d is 6-4s2. In Fe+3, 3d5 electrons. There are 5 electrons. Therefore, these electrons and the electrons present in the ligands also repel. So, electron-electron repulsions is there, and electron and central metal ion attraction is also there. Therefore, there are two kinds of forces. One is attractive force, second one is repulsive force. Attractive force between the ligands and the central metal ion. Repulsive force between the ligands and the electrons present in the central metal atom. Therefore, there are two forces. So, we consider the interactions between the central ions. That is, interaction is one is attraction, the other is repulsion. As a result of these interactions, interactions means both attractions and repulsion. As a result of these interactions, the degenerate orbitals of central metal atom disturbs. What is a degeneracy? Degeneracy means having same energy. Say if there are 3 p orbitals, px, py, pz, all the 3 orbitals are having similar energy or rather same. The same orbitals are called degenerate. Likewise, in the d block, there are 5 degenerate orbitals. These 5 degenerate orbitals get disturbed. That means the degeneracy is spoiled, destroyed. Therefore, look at this. As a result of these interactions, some attractions are there and repulsions are also there. Then the degeneracy or the degenerate orbitals of the central metal atom disturbs. That means the degeneracy is destroyed. Simply, degeneracy is destroyed. Now, as a result of this degenerate destroyed, then complexes in octahedral and square planar varies. The degeneracy is spoiled. The degeneracy varies from complex to complex. In octahedral complex, one type of degeneracy destroyment is there. In square planar complexes, it is another type. In octahedral, it is another type. Therefore, 3 types of complexes we consider: octahedral complex, tetrahedral complex, and square planar. We will first go with the octahedral complex. In first case, these postulates are applied to the octahedral complexes. First case. In octahedral complex, we'll consider the example like this. The M X6 plus or minus, right? What is M? Metal atom. What is X? Ligands. How many ligands? 6 ligands. Maybe cation or anion, sometimes maybe 0. So we are considering 6 ligands. 6 ligands are approaching towards the metal atom. Right? Now it happens like this. The diagram will be like this. CFT diagram, crystal field diagram. This is energy. This is state 1. This is state 2. These are called T2G. These are called EG orbitals. Under ligand's influence, now look at, this is called x-axis. This point is x-axis. This is y-axis. This is z-axis. So two ligands are on the axis, along the axis. Two more ligands are along the axis, and two more also on the along axis. So here, one point you have to remember, whenever you come across the octahedral shape, the octahedral complex having 6 ligands, all the ligands are lying on the axis of the shape. Now, keep this aside. Come back to d orbitals. There are 5 degenerate orbitals. You know very well. The 5 degenerate orbitals are dxy, dyz, dzx, dx square y square, and dz square. If you remember well, dx square y square and dz square are along the axis. Dx square y square and dz square are along the axis. I'll represent here. Look at the shape of this. This is a dxy. This is x and y. This is a dxy. Tell me, these are the orbitals. So dxy orbitals are between the axis. So dxy between the axis, dyz is also between the axis, dzx also between the axis. Therefore, 3 orbitals, dxy, dyz, dzx are in between axis. Dx square y square and dz square are along the axis. Therefore, 3 orbitals are between the axis. 2 orbitals are along the axis. This is the important point you have to remember always. Now, we consider the repulsion. The d orbitals are negatively charged orbitals. The ligands are also negatively charged. Therefore, these negatively charged ligands cause the repulsion. Which orbitals get more repelled? That means dx square y square and dz square orbitals get more repulsion. Why? Because they are along the axis. The orbitals along the axis and the ligands are also along the axis. Therefore, ligands and the orbitals along the axis get more repulsion. As a result, the energy of these 2 orbitals increase. That is why I have written here. Remaining 3 orbitals are there. What are the 3? dxy, dyz, dzx. These 3 orbitals are in between the axis. Therefore, the ligands do not have much repulsion when compared to the orbitals which are along the axis. That's why d orbitals undergo splitting. This is called crystal field splitting. Therefore, these 3 orbitals. Now tell me, T2G is nothing but 3-fold degenerate orbitals. T2G, nothing but 3-fold degenerate orbitals. dxy, dyz, dzx. These are 2-fold degenerate orbitals. dx square y square and dz square. So this is the diagram you have to understand. Now come back. Interactions important here. Completely electron-electron interaction. State 1, no ligands are approaching. All 5 orbitals have same energy. State 2, ligands are approaching to equidistant. The energy of orbitals all increases. State 3, the ligands are very close. Then the splitting starts. Previously, all the orbitals have same energy. So these 5 orbitals, energy is more, and once come here, the energy almost, this is the splitting of orbitals. The sum of these energies is equal to this energy. Because energy of orbitals does not change in any theory. If energy of orbital changes, The concept totally varies. Therefore, the total energy of the orbitals is same. Even after splitting, that's why it is written like this. This type of splitting is called octahedral splitting. This is simply represented as like this. Delta O. This splitting is called octahedral splitting. This delta indicates energy. O indicates octahedral. If I write T, tetrahedral. If I write S, square planar. Now, consider scandium, 3D1, 4s2, right? Scandium 3D1, 4s2. If scandium is in +2 state, it is 3D1, right? It is 3D1. How many electrons are here? 1 electron. So here also 1 electron. This 1 electron resides in the 5 orbitals. So if it is under the influence of ligands, I'll write this complex also. Scandium H2O 6 times +2. This is the complex we are discussing. Get the oxidation state. In this very rare oxidation state of scandium is always +3. For the simplicity only I am discussing here, right? So Sc +2, it refers to 1 electron. So this electron may be in any one of the orbitals. This is all discussion. And it goes to this level whenever ligands approach. And here 1 electron. Now, once ligands are approached to form a complex, let the complex is finished. Then in such a case, the electron will enter in the, because the electron always enters in the lower energy orbital. This is a simple point. The energy of the orbital, if it is lower, then the electron resides in. This is according to the above principle. Lower energy orbital gets filled, right? So this electron, so this T2G. So first electron has configuration T2G1, right? Second electron, these are the electrons. 2 electrons, T2. 3 electrons, T2G. 4 electron. Now, if 4th electron enters, then 2 chances. 3 electrons, first electron, second electron, third electron. If 4th electron is coming, then that 4th electron has 2 possibilities. Pairing may take place, or it may jump to this level. Pairing may take place, or it may jump to this level. That means 2 possibilities. For 4th electron, 2 possibilities are there. 2 possibilities. One possibility is T2G4 or T2G3 EG1. This is the possibility. So here, from 4th electron onwards, the question starts. That is, the discussion starts. So 4th electron may enter in here or here. No. Now the discussion starts here. If this energy difference is more, if energy difference is more, that means the splitting is more. The splitting is more depends upon the strength of the ligand. If strong ligand is there, then the splits more. Because strong ligand is able to donate the electron pair easily. As a result, the energy difference will be more. So this electron may not jump to this level. In such a case, what happens? The pairing takes place. That means pairing energy is less. Pairing energy is less when compared to octahedral energy. Right? So electron to be paired has less energy, then automatically pairing takes place. So if this energy difference is more and more, this energy difference is more and more, then pairing takes place. If energy difference is less, then the electron jumps here. So based on this energy difference, the electrons will reside there. That means there are 2 types of ligands classification, strong ligand and weak ligand. Likewise, you have to write the configurations. So now tell me, this energy difference depends on the ligands. Therefore, 2 types of ligands. These are strong ligands. These are weak ligands, relatively. This is called strong field. This is called weak field. These are strong ligands. These are weak ligands. This series is called spectrochemical series. Try to remember this series. Based on this series, questions may be framed. Only by knowing strong or weak, then it is possible to consider whether it is undergoing pairing or it is undergoing excitation. Now, if delta O, what is delta O? Octahedral splitting is less than P. P means pairing energy. Here, octahedral energy is less. Octahedral energy is less. That means the gap is less. The gap is less when compared to pairing energy. Then tell me, electron goes to this place or this place. If this energy is less compared to the energy needed to pair, then automatically electron goes to this position. Then likewise it is written, if delta O, octahedral splitting energy, is less than the energy needed to pair up, then the fourth electron goes to EG. Fifth electron also goes to EG. Likewise, different electronic configurations will be given. If delta O, that means this energy, splitting energy, is very high. It is very high. When compared to electron to pair up, then the electron pair up. So in this case, the splitting energy of octahedral is very high. That means field is very strong. Field is very strong. This field, ligand field is strong. Tell me when this is very high. When strong ligand is there, then splitting will be very high. Then in such a case, then fourth electron pair up. Then fourth electron pair up. So if delta O, splitting energy is less when compared to pairing energy, this is. If splitting energy more, then pairing takes place. This happens only in case of strong ligands. Therefore, this is in weak ligands. This is called weak field. This is called strong field. This is called strong field. Splitting. Strong field splitting or low spin complex. This is high spin complex. This is to be remembered. Now apply this. Consider this cyanide or carbon monoxide. Strong ligands. These are strong ligands. This is the order of the ligands. In our syllabus, this is the strongest ligand, carbon monoxide. Next is cyanide. Next is ethylenediamine. Next ammonia. Next EDTA. Likewise. If these ligands come, then what happens? Tell me. Then pairing takes place. These ligands come, pairing takes place simply. How? Instead of jumping the electrons to higher level, the pair up takes place, because in order to jump electron from this to this level, it needs more energy than the pairing. So it readily gets paired up. Or simply in strong ligands, pairing takes place. In weak ligands, pairing does not take place. In yesterday class, we have studied the valency bond theory, and some cases in nickel tetracarbonyl, the pairing has taken place. Look at that. They are called strong ligands and weak ligands. If electron goes into T2G, the energy decreased by 4 dq or 0.4 delta O. Decreased by 4 dq. 4 dq or 0.4 delta. If electron goes into EG, then energy is increased by, ante energy diagram ide kada, కిందకి వెళ్తే ఎనర్జీ తగ్గుతుంది, పైకి వెళ్తే ఎనర్జీ పెరుగుతుంది. ఇంక్రీజ్డ్ బై 6 dq or 0.6 delta O. Simple. Apply this. 5 electrons are there. 3 are here. 3 into 4. How much? 3 into 4. How much decreased? 12. 2 electrons are there. 2 electrons are going here. How much increasing? 2 into 6 plus 12. This is minus 12. Plus 12 and minus 12 becomes 0. The net becomes as it is. If T2G 3 system, crystal field stabilization energy. Crystal field stabilization energy is very simple. All the 3 electrons are here. 3 into, how much is decreasing? 4. Therefore, 3 into minus 4. Therefore, it is equal to minus 12. It is simply represented as dq. Right? If T2G and EG likewise, then in this case, crystal field stabilization energy is 3 into minus 4, which is equal to minus 12 dq. And 1 electron, 1 into plus 6 is equal to plus 6 dq. Therefore, net, how much? Minus 6 dq. If crystal field stabilization energy is negative, then that crystal is stable. Calculation of crystal field stabilization energy for different configurations. Different configurations. 1, 2, 3. In these cases, the configuration is T2G1. Here it is T2G2. Here it is T2G3. Now, 4 electrons, strong ligands. Weak ligands. Strong ligands, weak ligands. 4 electrons. Tell me, in case of strong ligands, the configuration is T2G4 because pair up takes place. Weak ligand T2G3 EG1. In case of 5th electron, in strong ligand T2G5. In this T2G3 and EG2. T2G6, T2G4, EG2. 1, 2, 3, 4, 5, 6, 7, 8. Next 7. T2G6 EG1. T2G6 EG1. T2G5 EG2. Next 8th electron. T2G6 EG2. Here T2G6 EG2. Now observe this. In case of 1st electron, 2nd electron, 3rd electron, and 8th electron, 9th electron, 10th electron, there is no difference in the crystal field stabilization energy, whether they are weak ligands or strong ligands. Reverse to the octahedral. All orbitals are in between the ligands, are in between the axis. But this is represented as a delta T. This is represented as delta T. This energy gap is definitely less than the octahedral. Why? In octahedral, how many ligands are coming? 6. In tetrahedral, how many ligands are coming? Only 4. 4 ligands energy is less when compared to the 6 ligands approach. Hence, the energy difference between the splitting is more in case of octahedral. Now, it can be compared like this. Delta T is equal to 4 by 9 delta O. This is the point you have to remember. This is the comparison. What is delta T now? Energy, splitting energy of tetrahedral. This is splitting energy of octahedral. The ratio between these two. The ratio delta T equal to 4 by 9 delta O.